All right, welcome everyone to our ninth Kubernetes meetup, and I don't know, third or fourth one at Red Hat. So today, cool. Let's start with just acknowledging having an acknowledgement for the country. So we respectfully acknowledge the tradition of the land of the Kulini nation and pay our respect to the elder past, present, and emerging. So tonight, we have two topics that we're going to talk. So tonight, Chris is going to talk about encrypting control planes, and Harrison, which is unfortunately unwell today and is from home, so he's going to present remotely, is going to continue his adventure on the Linux control groups. At the end, we will have a raffle and an open mic and a bit of networking with Q&A, and this time there's a bit of a change. After this, we're all going, a few of us are going to the Crafty Spire, which is just a pub around the corner, for a couple of drinks and continue the conversation. Cool, so if you haven't already, please follow us on LinkedIn. We're quite active, we post on a regular basis. And that's where we announce some of the things that is happening with the Kubernetes meetup. We also are on Twitter or X nowadays. And so first, we'd like to thank our long-term sponsors, which are JFrog, Google Cloud, CloudCasa, and of course, Cloud Native Computing Foundation for supporting us and allowing this meetup to run. And today, our event sponsor is, oh, nice logo, is Red Hat. Thank you for hosting us here and providing the food, and Code Cloud, which is going to, I think, distribute at the end there's 1, 2, 3. Ooh, yeah. 3 access. 3 months. 6 months. 3 lots of 6 months. 3 lots of 6 months. Cool. Of course, this event will not be able to run without our volunteers. So we're a bunch of us that are helping to organize this, preparing the slides, trying to bring speakers, and helping around on the day with this. And if you want to participate, there's multiple ways you can do this. Either by volunteering. We're always looking for people to help us, or if you have a company or someone which can help us sponsor the events or providing the food or the drinks, that would be great. And we're always on the lookout for speakers. If you have any topic related to Kubernetes, and you will see there's some topics tonight which are not closely related, are the foundation of Kubernetes, but it's a bit loose and a bit further away. Feel free to reach out and please come and talk to us, any of the 4 of us here. And I think I've missed anyone. Yeah, the 4 of us here, you can speak to us and see if you have a talk that you would be interested in giving. You see, it's a small community, it's a small group, quite friendly. So yeah, come and speak to us. So tonight we have two speakers, Chris Butler, which is from Red Hat, and he's going to talk about the encrypting of the control planes. And as I said, Harrison Liu, which is remote today, which is going to talk about the Linux control groups. So if you were there 2 months ago in this room, he was presenting some of the namespace functionality in Linux. That's a continuation of this talk. We have a couple of upcoming events. So K8SUG is present in Singapore and Canada, and we also have a UK one. I didn't know this one.
Yes, sir. Right. Yeah. Right.
That's new. Yeah. So there's next event in the UK in Australia is going to be at NAB on the 24th of January. So just after when everybody comes back. So that's going to be our first event there. So it's a big venue, so yeah, we can accommodate a lot more people. And we're giving away 15% discounts to our members. So if you register for the KubeCon Europe 2024, which is going to be in Paris this year. If you want to join, you will have 15% discount using the code which is at the bottom. So if you want to take a picture, I'll leave the screen on for a couple of seconds. Cool. And if you haven't finished, grab me at the end, and if you want to see the code. We're always looking for feedback as a way of improving. So if you have anything, please fill in the feedback form. But did I go a bit too far? Or is it at the end, this one? Yeah. Cool. Right, so let's go back again. Let's start with Chris. Tell us more about encrypting control planes.
Grab the screen and
do you mind joining on the Zoom, because we're recording it?
Yeah, sure. Yeah. You can have the audio.
Yeah. Given the
Share this to you. Good. Okay. Hopefully everyone can hear me. Cool.
over to you.
Okay, so this is something that effectively we're working on as a demo. So it's a demo between Red Hat and Accenture in Europe and Thales. So this is Thales, Thales are all over the shop. They build all sorts of military equipment, but really we're talking about their crypto hardware. So they provide HSMs to the market. So what we're doing here is showing how, particularly in the context of people who are delivering multiple Kubernetes clusters, they can provide isolation segregation between each of those Kubernetes clusters without blowing out their cost and get the rationalization benefits. So I'm going to talk through some of the underlying tech that we've been building, which has just been released into the latest version of OpenShift, so 4.14. Its name in OpenShift is called hosted control planes, but the name upstream is HyperShift. So if I alternate between that's why, because I was working with the upstream. So let me kind of talk about, like, why are we doing this? So one of the things that is not super huge here, but is definitely in Europe, is a bit of a resistance around some of the hyperscalers. So there's different markets. So, India as an example, parts all over different Asian countries, definitely France and Germany, where they're starting to build up their own cloud platforms. So generally people are getting to that IaaS layer pretty easily and consistently. We've got an offering in there, people using OpenStack, our OpenStack, upstream OpenStack. They're using all sorts of technology to get to that IaaS layer. It's when they get above that, they're starting to struggle in terms of delivering the same experience that you get with hyperscalers, because all of a sudden it becomes more complex. You're going from effectively 3 services, compute, storage, and network, to hundreds all of a sudden. So for us, based on a lot of learnings, what we, the 2 services which we see are really Kubernetes is at core. So you have some of the IaaS platforms are really built around Kubernetes as really the fundamental compute infrastructure they have. I know IBM Cloud's not a popular one, but I was involved in building some of the tech inside of it. And basically you go up and down the stack and all you see is OpenShift, just scattered in there. So the example that we're doing with Accenture here is they are using this company called Stackit, which is a German cloud provider, and they primarily provide on OpenStack. So at the moment, what they're doing is they've got patterns where they deploy OpenShift per client. Now, the problem with that, if you're deploying OpenShift on cloud providers per client, it's not so much us in terms of the licensing, it's that you're paying for 3 full control plane nodes where often you don't need it, but you're not heavily utilizing it depending on the capacity of the cluster. So that's their underlying cost, which they have to kind of bootstrap their services. And then the pieces which they care about, maintaining applications, delivering their security services is running on top. So what we really want to do is say, how do we decrease the cost of those clusters? And the way in which we do that is we introduce this technology called hosted control planes. So hosted control planes, I'll step into it a bit, has hosted clusters and the host cluster. So host cluster controls has all the control planes in there. And there's the reason why we're doing it. And this is something which we're actually using internally as part of our cloud offerings that we build. So Rosa has just released a version which is using hosted control planes. So the same technology we use to drive our cloud offerings we can use with other people. So we want to understand what the problem is or what the risks are. So the problem that we have here is there's a concentration risk that occurs. So when we look at a typical Kubernetes or OpenShift cluster, what we typically know is you have those control plane nodes where it's common for people to separate out the worker nodes versus control plane nodes. So you typically dedicate 3 VMs. So in our case, it's a 4-core, 16-gigabyte machine at the low end. You get 3 of them. Typically, it's 3 because of etcd. So you need a quorum. So you want a majority. So that means 3 is the ideal number. More doesn't necessarily add value to you. Usually, you vertically scale those nodes first before going wider. 1 you obviously don't want because you can't do any updates to the cluster without taking them down. So the challenge that you have when you have a typical environment for Kubernetes, what happens is the cluster admins and the developers use the same API endpoints. So you use RBAC inside the Kubernetes environment. So inside OpenShift, you define RBAC rules, which separate out what the cluster admins can do and what the developers can do. So that's okay when you're running a small number of clusters. And you see a lot of companies, there's kind of 2 patterns that we see in terms of OpenShift and Kubernetes in enterprises. One is they either have lots of small Kubernetes clusters, say develop a really simple RBAC model and just repeatedly deploy it, or they build these big monolithic clusters. So look at some of the government agencies that we work with. They've got these huge clusters that are running on bare metal, and I have 2 or 3. They might have 2 or 3 production clusters, and then I'll have 2 or 3 dev clusters, and that's it. And then they spend a lot of time doing Kubernetes RBAC. Now, that doesn't work when you're serving multiple clients because most clients don't want to share Kubernetes clusters. They want to have their own cluster. And there's some pretty solid reasons for that because no matter what isolation you do within the Kubernetes cluster, there's still things that you share. So you have to share the DNS. So no matter what you do, you can't attach the DNS to different networks easily. Everyone's sharing that same DNS, which means that in theory, you can look up what's happening in the other namespace, even if you can't get there. The other one is you share the same IP space as well. So everyone wants their own cluster. So what we do with hosted control planes is say, well, what happens if we host the control plane for another cluster inside a Kubernetes cluster? So you end up with this nesting effect. So I'm showing you one generation of this nesting effect, but there are partners of ours who do this in multiple tiers. So the service provider stands up a standard OpenShift cluster. So 3 control plane nodes, 3 plus worker nodes, and that acts as that root in terms of what you're doing. And onto that cluster, what they do is they deploy the hosted control plane. And what that means is you create a namespace, and then into that you dump etcd, the Kubernetes API server, in our case, OVN, all the network controllers, all of the controllers for your underlying storage interfaces, all go into that namespace. And then all of those get exposed via the APIs, via a standard load balancer. So what's really nice about that is in Kubernetes, the worker nodes, the API server never needs to talk to the worker nodes. The worker nodes only need to talk to the API server. with one exclusion, which is a kube proxy, but there's a good way around that. So what happens is we can deploy that, and then we can set up in a completely different environment the worker nodes for a tenant. So that's what happens when you look at our managed service offerings. When you look at Rosa on AWS or Arrow on Azure, we are now our next generation Rosa capability. In our tenancy, we use this hosted control plane capability to set up the Kubernetes APIs in this consolidated way, and then deploy the worker nodes into the client's tenancy. So that capability is also exposed for any of our clients to use. Actually, so I'm going to show you how this provisioning cycle works in a few minutes. So the reason why you want to do this is because you get a really nice compression benefit. So if you're running 10 clusters, you can deploy the worker nodes for 10 clusters in about the same, in this way, in about the same space that you could typically do for one. So that's a huge cost saving when you're running hundreds of clusters. The downside is all those control planes, which is where you keep all your secrets, are all in one cluster. So if you get breached, you're in trouble. So that's the trade-off that we're looking at. Because when you look at these sovereign cloud environments, the small scale cloud environments, one of the reasons why people do these is for, higher security environments, because they don't trust sending data to the Americans or to anyone else. So then you're kind of left with this issue of, I'm going to consolidate everything into one environment, and I'm going to trust it a lot for my high security workload. How do I make sure that each of these clusters are safe from each other? There's no bleed across them. So there's two areas where we can do this. So the first one is I want to be able to encrypt the data at rest and make sure the data at rest for the control plane is isolated between each of those clusters or between each of those namespaces, in this case, in a really strong way. And the tenants want to be able to control that encryption. So I'm going to talk about how we're doing that. Hopefully in the future, we'll be able to talk about what we can do in memory, because we've got some work going on in terms of what you can do in memory with confidential containers. But that's not quite ready for prime time yet. Okay, so I'm gonna just jump out and show you what it looks like to provision a hosted cluster. So I'm going to jump into, this is an OpenShift environment that I've got running in AWS right now. And I've got, in this environment, I'm running what's called Red Hat Advanced Cluster Manager. So you can see the control planes for two clusters. So you can see I've got this one, which is called the local cluster. And is that big enough for everyone? Or I'll make it a little bit bigger. Yeah, I'll try and make it a bit bigger. So I've got this one called the local cluster, and it says it's the hub, which is where that control plane is running. And I've got this one called prod, inventive name, where it's running the hosted cluster. So there's actually two different API versions that are running. So we're seeing both. So I'm not going to go into details on what is happening in terms of ACM. Really, what we're treating this now as a vehicle to deploy the hosted control plane operator or Hypershift. So what I'm going to do is I'm going to flick across and show you what it looks like underneath that in terms of the actual constructs that you see inside of Kubernetes here. So let's bring up the
ACM, so that's
Advanced Cluster Manager. Yeah.
Basically, offering custom manager.
Yeah. Okay. So if I just do, so if I go and do OC get, so we got a concept called hosted clusters. Actually, I could just to be clear, I can do this with kubectl as well. Okay. So what we can see here is I'm on a cluster. So first thing I'm going to do is I'm just going to say, get nodes. Okay, so you can see this is a pretty typical 3+3 cluster. So you got three control plane three control plane nodes, three worker nodes which are running all in AWS. You can see here, but you can also see I got this thing called hosted cluster. So what I'm going to show you is first, I can get across that cluster really easily. So you can see how this thing is managed. We're going to see where all the workload is running for the control plane. So this one's called prod. So there's a pattern to how this stuff works. So if I say OC get pods -n, and I'm going to say it's going to be local cluster prod. Local cluster prod. If I can type on this keyboard. What you can see here is in this namespace. So normally you'd expect this all to be in the kubeadmin or the open, in our case, some of the OpenShift control plane workspaces. Is you can see all these pods which are running, including a copy of etcd. Okay, so this is where it's the operator that we use here, which is called the hosted cluster operator, has deployed all the control plane components into this namespace, including etcd. And what I'm going to talk about, so etcd, as we mentioned, is where you store all your configuration information. So what I want to highlight here is if I go into OC get cd, now this will be a bit of a weird one, but if I go and search now for volumes, what you can see here, which is really unusual, is normally when you look at etcd, the only way it gets volumes is to go and just mount a host. Here, the persistent, the PVC claim that we have, if I ever go and have a quick peek into what this looks like and go OC get PVC, so this is our persistent volume claim, so where it's storing the data. Actually, you can see it here. So it's using a storage class. So for those who are familiar with AWS, it's actually using an AWS elastic block storage volume. So now we've provisioned storage specifically for this etcd storage and not using the host storage. It also has a nice side benefit, which is etcd's data volume is protected from the host storage, so you can't flood the system and kill etcd for the hosted clusters, because now each of these pieces has its own dedicated storage, which is a nice availability consideration when you're running lots of clusters. So that's kind of where we, just showing you what it looks like to, in terms of all the clusters, all that hosted control plane is there. We know we've got storage. The storage is not bound. So normally that storage, we can't encrypt it because you have a bootstrapping problem. So you can't encrypt the storage externally. The only way you can encrypt it is by the underlying host, because the Kubernetes API is not up until etcd is up, so it can interrogate what's going on. So you have this underlying issue that you normally have. Now we know we've got it separately, and we've got an external control plane which can control what's happening here. Any questions so far? Yeah.
About ACM, what's the connection?
So ACM in our case does two things that you're going to see. One is, it manages multiple clusters. So all we're doing is it pulls up multiple clusters. The other one is hosted control planes, which is a technology for building these APIs. It's a feature which you can enable in ACM. So if you are using OpenShift, you can turn it on from ACM and you've got a supported version. Otherwise, the upstream is a project called Hypershift.
Prerequisite to use ACM to
for this particular demo, yes, but you're generally going to be managing tens of OpenShift clusters, so it's probably not a bad idea anyway. But it is part of ACM in terms of the feature that we're using.
So how many clusters, because I think the limit here might be the number of elastic volumes you could mount on a particular node in AWS.
That's probably right. Depends on the underlying infrastructure. So there are 3 versions of this which are currently in the GA. So one is doing this on AWS. The other one is doing this on bare metal, where you manage the life cycle of the workers yourselves, which is kind of like a type none cluster. So I'm provisioning the control plane, and then I provision it elsewhere. And you don't have to use their storage volumes either. You can use anything else. So you could use, in our case, ODF, which is OpenShift Data Foundations. The other version of this, which we've made GA, which is primarily for people who are doing this on premise, is using OpenShift virtualization or KubeVirt for the worker nodes. In those cases, you're using a different, again, you've got choices in terms of what the underlying storage fabric you use. In OpenShift Virt, you can just use plain KVM mounts as well. What was it? Yeah. Okay. There's been tech previews in 4.13 and 4.12, I think, as well. I'd have to check about 4.12. Yeah, 4.13 definitely. It's been tech previewed. Okay. So what I wanted to show you quickly was what it looks like to provision a cluster in this environment. So we're going to do the cheat, which is when you install this, you also get a command line which you can install. So this is what I did. This is the same thing which I did with prod, but I'm going to use it to deploy a cluster quickly into AWS. So the version for AWS is a little bit longer. So it's saying in this case we're deploying 4.13. This is saying how many how many nodes I actually want to deploy. What's my base this is configuring the network constructs for AWS, storage sizes, what instance type I want to be. So all of this is kind of scriptable. So I do this, and if I just wait for this to go, yep, here we go. So this is now going to go and do some checks and pre-provision the VPC constructs in AWS. So it provisions VPC. It adds the extra routes to Route 53. It's putting the gateways in and the security groups that you need in for this cluster. And then once it's done, it'll start provisioning that control plane for us as well. So the control plane on this cluster will probably come up in about 5-10 minutes. The longer piece is actually bringing up the worker nodes. So it does actually have a side benefit for people if you're normally running multiple OpenShift clusters yourself. The provisioning lifecycle can be a bit longer. This can actually make it a lot faster for people who are provisioning, a lot of clusters here. So
Rose one's down to 10 minutes, or 15 minutes.
Yeah.
10 minutes.
Yeah, and that's because of this technology, effectively. So this is making this a lot faster. So I'm gonna let that run, and we'll come back, and what we'll do a little bit later is we'll go and switch context, and I'll show you where you can. One of the real benefits of this is if you've got teams who are not as experienced with Kubernetes, they can't go onto the control plane nodes and mess with them. So when you give them access, they have no control plane nodes to screw up. They can't actually delete etcd even if they wanted to. So that gives you like that nice security boundary in terms of what you're doing. Okay. So I'm just going to switch back to slides for a little bit and talk through the underlying issue that we have, or that we're trying to solve here with the guys in Talus. Okay. So what we said before is normally what's happening here is we've got this underlying Kubernetes API, so the one that we were just interacting with, which is on that host cluster, and that's backed by the host or cloud storage provider. And now the principal piece of state that we're concerned with is the etcd storage for each of these clusters and how we isolate these. So this piece of technology that we're using, it comes from Talus. It's called Talus. It's Cipher Trust Transparent Encryption for Kubernetes. So for people who are interested in this, there is a community version which is available on AWS. You can provision yourself and use. I'm not sure exactly what the terms are, but that's exactly what I'm using right now. So the Cipher Trust Manager, they kind of come in a few different flavors. For the really high security environment, they come in a hardened server, which is locked up, which you can't actually mess with, and it has a key management system behind it. So what the easiest way to describe what CTE does is when you provision a persistent volume claim for a pod, it kind of acts as a bit of a man in the middle. So it presents an API for storage, and which it looks like the same API would you be using underneath. And when you write a file to disk or read a file from disk, it's doing on the fly encryption or decryption with a key that's retrieved from the Cipher Trust Manager. And the keys have a short TTL, so they're about 10 minutes. before it has to go and pull the key again. So you can imagine in a high security environment, this is really good, because if you go and delete the key on the Cipher Trust Manager and go and kill a pod, then all of a sudden you have it restarts and you have no access to the data. So if you've got any issues in terms of, for us, what this is really doing is putting trust in an appliance where they've gone through an extensive security evaluation. I mean, we go through extensive security evaluations with our teams, but it kind of separates out the responsibility of what's running, because all that the Cipher Trust Manager is doing is deciding whether you can release that security key or not, or not. Nothing else is not a workload. So you know that it's only responsible for that. So it's got a really small attack surface. So we're using this Cipher Trust Manager. And what we're going to do is we're going to interpose it between the storage that etcd wants, so that it's encrypted on the way through and on the way back. So this is kind of what we want to be able to do. This is where we want to be able to provision a cluster. For each of those hosted clusters, we want to be able to have a separate key, make sure that those keys are isolated, and then the roles roll up into the Cipher Trust Manager so they can be accessed, and that each of them have different, that you can't go and delete other people's keys. So there's a few tricky pieces there in terms of Cipher Trust Manager, which we're still exploring. And at some point today, we're going to get up to the point where I haven't finished writing code. So we'll see how far we get. So that's what we want to do. The next question is, how do we want to deploy and orchestrate all this? So I'm going to get down to the weeds in terms of how some of this is done. So one of the other projects we're doing is validated patterns. So I'm mentioning this primarily because it's the vehicle which I use to deploy. I've been using to build this demonstration. And I'm sure we'll be able to share links just on public GitHub right now in terms of demonstration. So the validated patterns team, it's basically a reference architecture for deploying multiple components inside of an OpenShift cluster. So it's a bootstrapping technique where basically we use it to deploy OpenShift GitOps, which is Argo, in Advanced Cluster Manager, which is like a default anchor component. In this case, I've deployed hosted control planes only once, not twice, which is on the slide. Using KubeVirt, so OpenShift virtualization for when we're not on AWS, the Cipher Trust transparent encryption operator, and then cluster templates. So all of these components kind of got wrapped up into a set of Helm charts and Argo CD applications, which we deployed into this environment. So that's at a higher level how we deployed it. Okay. So now I'm going to kind of dive down into a bit of detail in terms of what does this thing actually look like in terms of how it works underneath? So this is where it does get a little complicated in terms of what we want to do. And I'll try and explain. I know it's tiny, and I'll try and explain it on the way through. So the object that we want to create when we deploy hosted control planes, it creates a custom resource definition called a hosted cluster. And what we're basically looking to do, normally when you run through this, what happens as a workflow is I deploy the hosted cluster, CR, the operator picks it up. It does two things. It looks at the worker nodes that you want to deploy and does a whole lot of stuff, which I'm not showing here. So if it's in AWS, it goes and starts to provision virtual machines. The other thing it does is it creates a namespace specifically for that operator. It deploys another operator, which orchestrates deploying etcd, the Kubernetes API server. If it figures out if it's on Amazon, deploys all the EBS storage drivers, deploys all the networking constructs as well. So that's the tool which we have. Now, the tricky piece about how all this stuff works, and this is kind of an interesting one on how these different vendor products work together, is we've built this where when you deploy etcd, you use a stateful step. Now, that's good because it makes sense, because you're deploying multiple, one or three replicas of etcd plus some storage. So you want to automate the provisioning of the storage and automate the naming of it. The downside, which is those things are immutable. And that was written in Go in an operator. And And what we need to do in this case is we don't just need to provide the name of a storage class. We need to provide a custom storage class per instance. So there were two choices we had. We either provide a custom storage class per instance, or we provided annotations to that PVC, which would pass through the information about what the cipher trust encryption operator needs to do. So in this case, what we've done is the way in which this all works together is there is a templating mechanism, and the templating mechanism allows us to abstract that hosted cluster one level above, which is using a thing called a cluster template. And what that allows us to do is start to add our own objects together. So when what happens now is when someone requests a cluster when someone requests a cluster, what they need to provide is a name and a type of the cluster. So in this case, I'm going to provide a name, which is, dev, and I provide a type of a cluster. In this case, the version we'll provide is a KubeVirt cluster as an example. So using OpenShift virtualization. When we do that, what we need to do is create all of these ancillary objects around the encrypted technology. So I need to be able to provision a storage class, which is specific for that cluster, because a storage class has references to policies and keys in the Cipher Trust Manager. So I use this Helm templating mechanism to say, I want a key. If I provision my cluster called dev, or in that case, cluster my cluster, it says, I want a key from a Cipher Trust Manager called, key for cluster my cluster. So we use this as a generic templating mechanism where we can provision all of the various bits and pieces, so we don't have to go and mess with the Hypershift operator. And the reason why is our SRE teams are dependent on it. I know IBM Cloud's SRE teams are dependent on it, and so is now AWS's, so we're not going to be able to mess with that. So we use this mechanism around it to provision it. And then the other one is the Cipher Trust Manager is controllable with Ansible. And what's a strange view of the world for an eventual is that you can actually use in our version of Ansible, you can create custom resources to run Ansible jobs and fire them off to the Cipher Trust Manager. So when you request a cluster, you not only request a cluster with all of these additional storage classes, then you say, hey, go and tell Ansible to go and create all the keys that I need on the fly. So that's the way in which we're kind of orchestrating this whole lot together. So it ends up being a nice process, because in the end, if you're a tenant or if you're like a DevOps team, all you need to do is create one object, and you can put quotas around it inside of Kubernetes, and all of a sudden you've got a cluster which is spun up, and it has its own encryption keys, and those encryption keys map to something in Cipher Trust Manager, which is an external key management system. So that's what it kind of looks like at a Kubernetes level. I will say at this point, there are a few potential there is risk of a roadblock, which I haven't found yet, but this is the latest state of affairs as of Friday at 7 p.m. So, so Cipher Trust Manager is not this where it's been built in the open. So it's in my GitHub repo, and you'll be able to play with it. So it's built on the hosted control plane piece, which is part of OpenShift product, but there is an upstream which is called Hypershift. And the templating mechanism, which is the cluster templates operator, is an upstream Red Hat project, which they're looking at folding into Red Hat products. So it's upstream of Advanced Cluster Manager, but it's not in there yet. So a decent chunk of that is all upstream. The Ansible components, I would have to check exactly what was upstream versus product. I'm using the product in this case, but that's just because it was the easiest thing for me to consume. Okay. So I think that most of this would be so the piece which is tricky is what is interacting with ACM, because there are some interaction. specifically on provisioning the worker nodes, it leverages some of the other APIs which ACM uses. So it uses Hive to provision worker nodes in AWS. So those components, you'd want to do a deep dive in terms of finding out how many other upstream pieces that you need to pull through, because it's using this background, which is ACM has already existed in product for us for a while. The version for OpenShift virtualization, or the Kubernetes virtualization, if you're doing this on-prem, that would map to KubeVirt primarily, and the HyperShift operator. I mean, I'm not sure if you saw before, but when you looked at the command line is still called HyperShift, which is the upstream version of the CLI. So does that answer your question? Yeah, cool. So what I just want to finish off by doing is saying, let's go and have a look in what does it look like to go and get into that hosted cluster from where we were. Okay, so I'm going to go back into OC get hosted clusters. So I think I created one called dev. Okay, so it's saying hosted control plane is available. It's the system is available. So I'm going to go in just to have a look at this thing in detail. So I can go in and see. So when you go in here, you can see where the control plane has been spun up. You can see, in this case, Ignition is used by CoreOS to bootstrap the worker nodes. You can go in. So what I'll do is I'll go and grab the dev admin kubeconfig. So I'm going to go and grab this secret, which is inside the hosted Kubernetes cluster, and then we'll flip context and we'll be able to see the context that you would see if you're a user on that cluster. So that secret is what you would send to a cluster admin, and you'll see how limited a view that they have right now. Okay, so I'll just go and get this quickly. Oh, secrets. I'll start. Damn it. Yeah.
What is Ignition in this?
So Ignition, Ignition is an API, which basically it's a bootstrapping technique. So it's similar to CloudNet. So it's basically when you boot up the server, you can point it to an Ignition server, and that Ignition server feeds it metadata around how to configure the node and the underlying OS. So yeah, I got that right. So you can, I'm just gonna supposed to get it's a field, right? No, it's okay. I just need to get the data. So if I see YAML like so we're gonna see how good my memory is right now. Yep. Okay. Dev. Export. So I'm just gonna set that, override that kube. I'm gonna put that dev config in here as my kube config. Okay, and if I OC get nodes. Let's come up. Okay, so you can see here, I provisioned one node. So I've got a one worker node cluster. And if I do an OC get pods -a, you won't see much. So you won't see much. You'll still see a lot because it always provisions quite a lot. But what you won't see in terms of connectivity, in terms of what's happening is you can't see etcd. So you can't see the core Kubernetes control plane components. You can only see the components which are deployed as a daemon set onto the worker nodes. So the real one you want to look for here, the only really different thing in terms of the architecture here is this component called connectivity. And so you'll recognize most of the time the worker nodes are going back to talk to the control plane nodes. The only exception to that is when you go and say, give me a kube proxy to get to a service which hasn't been exposed yet. And the way that happens in this architecture is a component called connectivity, which allows you to establish that reverse proxy, but it does so by basically establishing a persistent connection back from the worker nodes, which is ongoing, and then you can travel back across that now. So that there you can kind of see the cluster. I'm now on that cluster. I only have one worker node, which is also great for development environments for your self-hosting, because now you can provision a cluster with one worker node and almost zero control plane node costs compared with what you're doing if you're doing it on bare metal or on virtual machines. So you got less overhead cost. And while I didn't show you the encryption yet, because it's still a bit of a work in progress, I think we're probably almost timed out.
Running the worker node.
Yeah, all of those ones are, because it's also it's bootstrapped up some of the components there. So it's running here. You can see it's what you can see there is it's got the cluster. It's also deployed into that environment, the control plane for ACM. And in that case, it's also deployed GitOps already, because I pre-configured the cluster to have a little bit of workload on it. So you can see it's got work which is in there, but most of it, none of it is actually workload yet. So some of these are components which have to be there. So if you look at any cluster, when you look at depending on how much you're carrying, there'll be quite a bit on there already.
So usually an OpenShift cluster has like 30 operators that make up the base OpenShift offering. The bulk of those operators are now moved into that shared control plane. So it's not just your standard Kubernetes control plane, which is your API server and your scheduler, etc. You've now moved about, I don't know, probably 25 operators are now in that shared cluster, you know, in that one namespace per node cluster.
Yeah, I mean, I'm not sure how many people are devs versus operators of Kubernetes. The other real great benefit is you've just decoupled the worker nodes API version or the worker node OS version from the API server OS version. And so when you have any issues around security vulnerabilities, the one that people really are concerned with is if there's any API server vulnerabilities, and you can upgrade those independently of the workers, which means that you don't have to talk to the people who are running workload on that to make sure that you can secure it, which is good.
Yeah, and there's one other thing to say about Rosa. So in the managed service, I believe the ingress components in that shared namespace are actually spread out on a dedicated set of nodes. They're tiny nodes that AWS provision for you. So it just was a security requirement from AWS. So the actual ingress components of that shared control plane are split out per custom.
Oh yeah, that's required because of the VPC network architecture. Because otherwise you're deploying it onto into our network. No one wants their data plane to be flying via our network, and we definitely don't if it's running workload, because then we're paying for the egress fees. Any other questions?
You should 3 control plane nodes.
Yeah.
In the hosting cluster.
Yeah, you can select between 1 and 3.
Okay.
So if you go back, it was actually saying single availability.
Okay.
So in that cluster there, what you actually, the real thing you don't see is as a cluster admin for the hosted cluster, you don't see the control plane whatsoever in terms of the nodes that are running on it. You only see your workers and what's running on those workers. On the hosted side, you also have a choice by default to flip between 1 replica and 3 replicas of the component. So I can either have 1 etcd pod running, or I can have 3 etcd pods running, and they're on a quorum. When you've got 3, node like Anti-Affinity will spread them out across the worker nodes by default. So, I mean, we're doing this, so this is like the actual hosted control plane piece is like a collaboration between the IBM guys, where they use it for IBM Cloud, and they running clusters of 200 nodes, hosting thousands of clusters in their environment. So they're really running this at scale already. So even though it's new for us, it's kind of been, but
originally IBM technology.
yeah, there was that and they also do it where they run 3 or 4 tiers of this hosting. So basically inside a region, they run their own, the clusters which they use to host client workload have a hosted cluster which hosts their control planes, and then they have a global one as well. So you can effectively keep on nesting this as far as you want to go, assuming you're happy with one, depending on the number of central points of failure you want. Eventually, you want to start spreading it out if you're running a large enough network.
There's a proxy to the Cube API. So do you want that across several nodes in the?
Yes, that's everything. Yeah, so that all of those. Yeah.
Aside from that.
Yeah, it's really just the connectivity, and that runs per node, effectively. So you can just run it as a lightweight proxy if you need to. Yeah.
Okay, thanks, Chris. That was a great presentation. We're going to, sorry, just need to put my mic on again.
Do you want
Yeah, I'll need this. We're going to go with Harrison's presentation, and we'll see if that works, because I'm afraid there's no. Can we go on the? We have sound on the.
There should be sound somewhere.
Hey. Harrison.
Yeah, go ahead.
We can't hear you. Give it a try.
He can hear us.
Yep, that's good. Harrison, can you talk? See if that works.
Okay, how does that sound?
Hold on. So that might be on Zoom. Give me a second. Can you give it a try again?
Okay, how does that sound?
Oh, that's very loud now. Give me a second.
Okay.
We need to slow it down.
No worries.
Where was that? Go ahead.
Okay, how about now?
Great, perfect.
Okay.
Cool. I'll hand it over to you. Can you take the share your screen?
Yep, no worries. Give me a second to set this up.
How do I stop sharing?
Okay, I believe the screen is sharing, and just give me a confirmation. I'll just go ahead.
Hold on, I'm just moving it to the. Cool, go for it.
Okay, sure. Hello, everyone. I'll be quickly going through a very high-level summary of Control Groups version 2. So in the past, we talked about something called NICS namespaces, which is controls the visibility of specific system resources, such as processes, files, and users. The distinction between namespaces and C groups is actually quite subtle, but really important. So as I mentioned before, namespaces deals with visibility. C groups deals in terms of resource control. For example, how much resources could I have? For example, CPU, memory, or the consumption of certain disks and devices. It should also be noted that C groups are also a form of namespace, but in a lot of modern implementations of containerization, we don't technically touch that. Just some quick history of basically what control groups are. Basically, it was designed by a bunch of engineers at Google. Was part of experimental effort for containerization around the year 2000. It was largely redesigned by Tejan Hill at Facebook around 2014 and merged into the mainline kernel, that is V2, by around 2016 to 2017. And that's pretty much a high-level history of basically what it is. Basically, now the important part is basically how Kubernetes uses control groups. So two things which is really obvious is that the first thing is that it's a form of resource management. One possibility in the past is that without C groups, a poorly designed container could potentially hog up entire system's resources, assuming there are no safety rules. So what will happen what will happen is that essentially high amount of CPU RAM being used. It will reduce the quality of service of a specific node or cluster. Therefore, basically it's just really bad for everyone. Another thing is observability, in the sense that C groups could be used for observability to a degree. Oh boy, what was that? Okay, moving on. So very quickly, I will show you a demonstration of basically how Kubernetes, or basically Meetup, uses control groups in a high level. So what I have here is a very simple YAML configuration for a simple example pod, I guess. kubectl plot. Let me just show you what I have here. Very simple configuration. It creates two containers. The image is Ubuntu, and basically runs a very simple command that just sleeps for 30 seconds continuously. So what I'm going to do is I'm just going to apply this pod. Excuse me. And from there, I'll just log into the Meetup virtual machine. A few minutes to load. That looks good. So basically what I'm doing here is just I'm trying to find the exact process which these VMs are, well, pods containers are running on. And from here, what I could do, I could access the proc fs file system. Proc PID, let's call it C group. And from here, we could see that it's actually generating a bunch of C groups. These are actually generated by Kubernetes itself for a particular pod. So this shows you that, at a very low level, C groups are commonly used by Kubernetes out of the box. To show this wasn't generated by me. In general, a lot of the basically system processes, for example, PRD1, usually have these kind of destinations. So that's kind of like a motivation factor to show that basically Kubernetes is technically using C groups. And this is why I'm kind of just talking about these kind of things in a Kubernetes talk. Now, moving back to the slides. So now we kind of gave a high-level motivation. We're going to talk about very smaller units of what a C group comprises of. The most important part is its controllers. So the controllers are the subsystems which make up of C groups. They individually control things such as CPU use, memory use, and other aspects of C groups. From this command here, this just listed some very basic controllers that you actually set. CPU set allows, it's quite a common thing to do, which basically allows you to designate a process to be run on a particular CPU. CPU is usually used for rate limiting or increasing the amount of CPU use for a particular process group. IO, obviously for input and output. Memory, quite obvious as well. Rate limiting how much memory you use, and PIDS, which essentially limits the amount of processes you could actually create in a particular C group. The PID C group, why it exists, one of the easiest definition reasons is that basically it prevents fork bumps. So basically put a limitation amount of PIDs you could create in a particular C group. Once that limitation is reached, the kernel will just tell you you cannot create any more processes. So it's quite an important C group in certain aspects. So let's move on. So another point you want to make is I'm actually talking about C group v2 here. There's a command you could type into your terminal to check what type of C groups you're using. If it's actually showing some sort of temp file system, that means you're probably using C group 1. A lot of the earlier operating systems use a combination of C group v1 and v2 together. They could work interoperably, so it isn't yeah, because they allow for backwards compatibility. That's what I'm trying to say. And if you look at even earlier systems, they probably only have C group v1, which is typically not common these days. In the future, what's the idea is that basically everything's all going to be consolidated into a single control group v2, so C group v1 will no longer be used. So now I'm going to quickly go through how we use C groups v2. The easiest option is to essentially use the sysfs file system. So basically, you could go to sys/fs/c group, and basically you could just echo stuff into it. Now, in container management and Kubernetes, nobody really uses these, but this is one way to use them, a very quick and dirty way. Now we talk about basically what a C group is. Let's look at basically what it kind of looks like at a high level, a hierarchy, I guess, the C group file system hierarchy. So in general, it works in the file tree format. You could have, multiple C groups layered on top of each other. So for the example here, the root C group, which is, the root FSC group, could have multiple children, and each of the children could have multiple subchildren. As for basically the C group controllers and C group subject control files, these files essentially tell us what kind of controllers or basically small units of subsystems that this particular C group has enabled. So for example, in a root file system, we have CPU IO memory.pids. This file here tells us essentially what the child C group will have enabled. So we're going to enable everything for these two C groups, but for the child C group of a system.slice, we're only going to enable CPU IO.memory, and therefore the C group controllers files will actually reflect that as well. So now I'm going to quickly demonstrate how to do this in a terminal. Clear. So I'm already, please note, I'm already a root user and I'm already in this sysfsc group directory. So to do the easiest way to do this for demonstration purposes is that we could just essentially echo the PID of a shell and shove that into a particular C group. Since we haven't created any C groups just of yet, I'm going to create one for our demonstration purposes. Let's call it my group. So basically what I did here, I just simply created a directory in this particular C group, or basically from the root C group. And if I do this, the stuff is already automatically populated for you. Clear. So currently this C group is empty because if we go here and do a prox, there's no output. So therefore there's no processes currently basically allocated to this particular C group. So to change that, basically what we could just do is put in the echo command and just write. We could just write 6911 group.prox. Give me a second. There we go. So now we actually populated a C group with a PID, or basically a process of this particular bash or basically shell session. So let's have a look at what's in this. Now, you may actually see two PIDs. This is intentional because the cat command basically creates another process. So basically what happened is that the parent process, if a parent process belongs to a particular C group, the child process will also belong to the same C group. So if I do this again, you realize we've generated another process, and that's another cat process. Okay, that's basically how you create C group, or basically associate processes with C groups. Now we're gonna talk about how to different types of controllers down to, well, basically restrict the amount of controllers being sent down to separate C groups. So as I mentioned before, we have a file called cgroup.controllers, which cgroup.controllers, which tells you different types of C groups in existence. But if I do cgroup.subtree control, that should populate something, but it's currently not been populated. So basically what I'm gonna do here is I'm gonna echo, let's say we want to get rid of a CPU. Let's say we want to add a CPU control group to the subtree control. So basically we want to tell the child C group, which we're gonna create, to have CPU controllers. We could just do echo CPU C group subtree control. And now if I make a directory, test grp, it should tell us that we have all the CPU controls. But please note, there are no memory controls or anything like that, because in the file C group subtree.control, we only have CPU. So let's say we want to restrict the CPU controller for this particular C group. All we need to do is from the parent group, write minus CPU to the C group subtree.control. And from there, that should automatically update. I notice there's a couple of entries disappeared. Since the child C group doesn't have any PRDs assigned to it, so let me just show you what I mean. Test grp C group .prox. This means we could actually remove this C group quite easily. I am dear. However, if I try to do this into the group with the process already assigned, excuse me, that shouldn't work because we have a process assigned to it. Therefore, removal of that is not possible. Let's go back to my group. And this just shows you the basic creation and also process assignment and permissions that C groups already have. Now, moving on. So I'm going to demo two different types of C groups and how they kind of work. So now I'm going to talk about the memory C group, which is a quite important, well, I guess the second most important C group in existence, well, in my opinion at least. So here's just like a few important definitions of basically what each of the I guess the files kind of control. What we want to discuss today is the memory.max thing, which is essentially a memory hard limit. Once this limit is reached, basically what's going to happen is that the system will try its best to optimize the program out of memory. If it's not possible, what's going to do is that it's going to invoke the system's out of memory killer. And from there, basically what it means is that basically you'll just arbitrarily start killing processes. There's also memory.high, which is like the throttle limit. So basically, once this limit's reached, usually what happens is that it will be placed under very heavy pressure to be shifted to the swap. So this is essentially a limit where swap becomes very aggressive if you have swapping enabled. So now we're gonna go through a very quick demo. Here. So we already created this. We're gonna use the same C group. So let me look at memory.max. It's currently listed as max, so therefore there's no limits on how much memory we could use, subject to system constraints. Now, let's make some changes to that. So what I'm going to do here is I'm going to, that's the wrong one, going to essentially tell this particular control group that basically you're only limited to 1 megabyte of RAM. Now what I'm gonna do is I'm gonna essentially execute a program that actually generates 100 megabytes of RAM. Now, you may be wondering, why isn't this being killed? It's quite obvious. not obvious. Essentially, what's going on is that the operating system realized, hey, we can optimize out most of the memory consumption. So let me show you what I mean. So here's the 100 megabyte program which I run. Vert, that kind of shows roughly in line. So we're using about 100 megabytes of virtual memory. However, shared memory and RES are, well, that's just RES are relatively limited. If I don't have this limit, you'll probably be using a much, these two values should be a much higher number, but because the operating system realized, I'm not really doing much. I'm just asking for 100 megabytes of memory, just writing the same thing over and over again to it. Therefore, what it's doing is just basically optimizing basically all of that out of the system. Therefore, that won't actually evoke the other memory killer. However, if I do this a couple of times, as you can see right now, the OM killer is actually doing its job. It's actually killing the older programs which I actually created. So if I go to the message right now to have a look, as you can see, OM killer has been invoked and basically start killing processes. So what I want to show here is that basically I want to demonstrate that the limit layer is actually a hard limit. Although the operating system will try its best to optimize things out and prevent this hard limit from being reached, it is also not particularly, it is actually quite particularly useful. Moving on. So now we're going to talk about CPU. So going to use the same C group, but first let's undo what we did. So now we should be returned to max memory. We still got like a leftover program running. As you can see right now, the RES suddenly went up to about 100 megabytes. Let me just kill that process very quickly. Yeah, there we go. Clear. One last thing I want to demonstrate is very simple one as well. So what I'm going to do is I'm going to create a program which uses 200% CPU. Keep in mind, 100% CPU is one CPU. So therefore, 200% CPU means I'm using a multi-threaded program that's using two CPUs. So basically what I'm going to do here is I'm going to do thread. There we go. Now it's running this thing. As you could see on top, the program here is using about 200% CPU. Now, let's make some changes, shall we? Right, let's run this in the background. And what I'm going to do is I'm going to use something called CPU.max to actually limit the amount of CPU which this particular process could be allowed to use. So what I'm saying here is that for every 20,000 microseconds, so for every 20,000 microseconds, right, out of 100,000 microseconds, this is the time that basically a particular CPU, this is the time available for that particular CPU. So so basically out of a period of 100,000, 20,000 will be used for this particular process. So once I execute that, what's going to happen is that the CPU usage will drop immediately to a much lower value. As you can see, it's doing it right now. And it has dropped off the, because he exited, but let me just quickly demonstrate that again. Yeah, it is. Its CPU is about 20%. There's also another way to control CPU usage, which is called CPU.max. Essentially gives you the same effects, but essentially on a CPU.wait, which basically allows you to give you the same effect in a way that basically each C group will have a potential weight, and basically the completely fair scheduler in Linux will essentially schedule CPU time based on that. Other than that, that's pretty much all I have for today. There's a few other more advanced topics here by basic delegation and thread mode. Delegation, it essentially allows you for like non-privileged users to make changes to certain C groups, because keep in mind we did everything mostly using the root user. And thread mode, which allows for task level granularity when it comes to assigning certain behaviors to certain threads. So you have different threads in different C groups if you really wanted that. That pretty much concludes my talk, and yeah, that's all. Is there any questions, or we're good?
Is from anyone here? I'll relay. Yes.
Yes, I'm pretty new to Kubernetes. Can you please explain to me what the controller is?
Okay. Please note, this isn't Linux C group controllers are not what you call Kubernetes controllers. These are two completely different concepts. So is my mic on? Just checking. Oh, it is on. Yeah. That's good. So for Linux controllers, so Linux C group controllers, they're more or less a very low level subsystem that allows for basically enablement of certain system resources. So as I mentioned before, CPU is a type of controller in C groups. Memory is also a type of controller in C groups. Kubernetes controllers, completely different thing. Just ignore what I said about controllers if that's a bit confusing.
Any other questions? Cool. Thank you.
All right, thank you.
Thanks, Harrison.
Thank you, Harrison.
So we're going to do a quiz to see if you followed what happened tonight. If you learn anything, to test your knowledge. And I mean, if you've been with us a couple of times, you've already seen this. Come on. Just need to restart this thing. All right, so you will see a QR code popping up. If you can pull up your phone, register. So what are the prices?
We'll get winner from the top, and to have the priority to choose the takeaway.
Cool.
Yeah, we have a three.
Another. Wait. There you go. That's the one. And I will start the quiz.
6 months free access to Cloud Code.
So you will have 3 months. So there's 3 for the first 3.
One for each winner, okay? Not 3,
So,
one winner.
1 for each winner. So you'll see there's a leaderboard. So based on the questions are based on what you learned tonight. And based on that, the faster you answer the question, and if you answer right, there will be a leaderboard. So if you have not done it yet, you will see there's a leaderboard that is going to come on the screen. And at the end of the few questions that we have, the winner, so we'll go from top to bottom, so from first, second, third, and so on. The first 3 will have access,
But you
can choose.
Yeah, you have to. You got a priority to choose anything you want. We have
Okay.
3 free 6 months.
Free 6 months access to Code Cloud.
Swags here to take away. Yeah, it's up to you.
And everybody gets a cap on the way out, so you don't have to. That's a gift.
For each of you.
Yes. As many caps you want.
Randomize the options. Randomize the option. Number of questions.
Yeah.
Stuck.
Okay. Okay, hold on. It's not ready.
Also has the QR code.
There you go. Everybody ready? Okay.
We can see the person.
So there's, yeah, you can see the leaderboards on the right hand side. There's a few more names that need to be coming. Hey, you know that, how to you?
You're not allowed to join.
You wrote the questions. I think there's a few more registering. So you will have 10 seconds to answer each questions. More? There's more. Ah, okay. So there's a few more questions. So there's 30 seconds for each question. But the faster you answer correctly, the more chance you'll be on the leaderboard. Are we good to go?
Can you share the screen on Zoom?
It is not on Zoom. Should be
Yeah, it's for the access.
yes. Okay. Ready? All right, let's go. First question. I said first question. Coming up with 3, 2, 1, and go. Which component is responsible for encrypting data at rest? Kube proxy, etcd, kube scheduler, kubelet. When you select it, you yeah. All right. Cool. So the correct answer was etcd. Cool. Everybody ready for the next question? There you go. You want cool. In a standard OpenShift cluster, why can you not completely encrypt etcd excluding at the host OS? It's a bit too small for me to read. Cool. Because etcd cannot be encrypted as it's bootstrapped components. There you go. Here is the leaderboard. So Rowan still leading, or is the leading one? Cool. Next one. 3 more questions. Cool. What do control group do? Cool. So the correct answer was control the rate of the system resources consumption. All right, 2 more questions. Ready? 3, 2, 1. Cool. Which company is responsible for the inception of control groups? Google, IBM, Red Hat, Oracle, Microsoft.
It's obvious that at least I won't expect 100% answers this time.
And the correct answer was Google. I know we had Red Hat. That was a bit confusing. That was a trick. All right, final question, and then get ready. 3, 2, 1. Boom. What does the C group file memory.max do? Mandate the maximum memory consumption of all processes within a C group, tracks the total memory usage over time, define the minimum requirement memory for system startup, control the memory allocation for kernel processes, and set the memory usage threshold for triggering swap usage. I didn't pay attention. And the correct answer was mandating the maximum memory consumption for of all processes within a C group. Cool. All right, let's end the quiz and see who is the winner now. Cool. David. Who is David? Hi, David. Well done. Congratulations.
So do you want to come over here?
Yeah, you want to.
Virtual one, you have free access for 6 months and then
For free access, with your email. So what's next?
Rowan. Who is Rowan? Hi, Ron. Congratulations. Well done. So same, if you want to come, you have the choice between either some of the goodies over there, or you can choose one of the 6 months subscription to Code Cloud, which would give you some training on Kubernetes. Okay, while it's happening, now the third place, Micho. Where is Micho? Hey, congratulations as well. Well done. So same, if you want, you have the choice between 6 months access to the Code Cloud, or one of the t-shirts or one of the goodies. So up to you.
Get the whole list. Yes. But when you skip because they are no.
Yeah.
But good job. Good job.
Oh, do we stop at the third or?
No, we can go.
Oh, we can go. Okay. There's a few more goodies.
Yeah, for more.
lots of chances.
Yeah.
Lots of chance.
Lots of chances. So next one, exclamation mark P. Hello, our exclamation mark P. Congratulations. So same, you have the choice in the 6 months subscription to Code Cloud or one of the goodies. So there's one more spot. One spot left. Okay, yeah. The fifth one. Thiago. Yeah.
No, I'm just for the competition.
You just saw the competition. Ignore this one. So on the 5th or 6th position, 6th place, Varghese. Hello, congratulations as well. There's a few goodies left, or there's one 6-month subscription to CloudCloud, access to CloudCloud. So, oh, okay. Hence the good the good answers. Nice. And 7th place, Trent. Congratulations. So same few goodies or the last 6-month subscription to CloudCloud.
Access or done. Only the good example.
Yeah, so at the end you can go and come and grab some stickers.
Okay, we have one. Oh, we have one more. Yeah.
Okay. I feel good. Who does feel good? Congratulations as well. Siva. Hi. Congratulations. So same, either that or we still have one subscription left. Okay, well, we don't have any more. There's a few socks or goodie. What else?
Yeah, we have goods just for
Nice. So 3 more. So well, I guess I'm going to do a bit faster. So Austin and Prashant and Hermantha, congratulations to 3 of you. If you want to comment, there's three goodies left.
The rest of the 5, and also we have a good total.
Yeah, cool. With the rest of the
It's like the feedback form.
yeah.
Yeah, we can hang
Cool.
out at the cloud if they want.
Yes. Cool. So just last thing to do before we head to the pub. So if you can take a few minutes to fill in the form for the event, that always helps us to improve and see what we can do better. That would be very appreciated. Yeah. Ignore the swag part. We're doing the quiz instead.
Let's go for photos. Yeah, let's
The one I presented, yes. The one we have a recording, so the recording will be available in a couple of days. Usually on on Monday.
Post in LinkedIn, so just for us, yeah, stay tuned. There will be no slides.
You should see the slides because we record the screening and what they said.
Okay.
Yeah, they submit the slides as well. Yeah. Okay.
Oh, great.
Yeah. Welcome.
I haven't been able to catch up.
This one was a bit advanced, so yeah, that's okay if you feel lost. Okay, so we have two things. So if you have any, so we just have a few minutes for open mic. So if you have anything to say, like if you are recruiting or having or looking for a job, that's probably the right time in the Kubernetes space. That's the right time. So if anyone is interested in anything, no, okay, that's fine. And just like one last thing, let's head over at the front for just taking a group photo that we post usually on our Meetup page. And then we are going to head to the Crafty Square, which is just around the corner. So either you wait for us and we all walk together, or whoever is impatient to have another beer can go there straight.
Yeah. Volunteers. Okay, so would you mind if this with the consent to me? I will send something.
Want to move at the front? Yeah,
Oh.
you're taking the authentic picture. You're taking the picture.
You want to get in? I'll take the picture.
Thanks everyone online. See you later.